Hey folks. Okay, picking up where we left off with Tool 10, right? Um, for all the reasons we were talking about before, it's helpful to know about the nature of light and what kinds of light you can see in the whole electromagnetic spectrum. So, let's fill out our spectrum here, right? Use the information below, fill in the table below with what types of light and one use for the light. So, okay, what's one use for visible light? Well, what what use do we find visible light? Well, it's the type of light that our eyes see. So how is visible light useful? Well, we see with it. So I'm going to say seeing is pretty useful, right? Um, shall we lay this out? And I didn't tell you exactly how to lay this out, did I? I didn't say you had to do it one way or the other, but let's do it the same way we were doing it before, right? Where the long wavelength end is over here, and the short wavelength end will be over here, just like we had the spectrum in Tool 10. So long wavelength, short wavelength. So then what's longer wavelength than visible? Infrared. And then longer than that is the microwaves, and then the radio waves. And the radio waves are the longest wavelength part of the spectrum, right? And then shorter than visible light, what's shorter wavelength than visible? What's bluer than blue? What's more violet than violet? Ultraviolet. And then shorter wavelength than ultraviolet is the X-rays. And even shorter than that are the gamma rays. All right. What use do we find infrared? Well, like we said here, right? That infrared, low power infrared can be used to send a signal, right? If you have a remote control, you can check this out too. If you have a remote control with a little like light bulb or emitter on the top of the remote control, then when you push a button, that remote control signals your TV using infrared light. Infrared light is also given off by, well, if you can, what do we call infrared vision? If you can see in the infrared, we usually call it like heat vision, right? Because hot objects give off a lot of infrared. And so if hot objects give off a lot of infrared, then you can emit infrared and your body will feel warm. It will be useful as a heat lamp. Or I should say heat lamps give off a lot of infrared, because they're hot. Or you could have like an infrared camera where if you don't care about what your camera sees in the visible light, because let's say you want to see things at night. Well, if you're looking at night, then warm objects like, animals, people, warm-blooded animals, right? We're warm, and so we give off infrared light. And so if you're looking through an infrared camera, then warm things like these light bulbs over here, or like people will glow in the infrared. What use do we find microwaves? Well, your microwave oven works by emitting light in the microwave part of the spectrum that specifically excites water molecules. Right? That's how a microwave oven works. A microwave oven only gives off light at one wavelength, just the right wavelength that spins water molecules. And when you spin and excite water molecules to get them moving faster, then they're gonna heat up. And so when the water in your food heats up, it heats up the rest of the food too. This is kind of why when you cook something in the, when you reheat something in a microwave, if you have leftover pizza, right? You have leftover pizza and you put it in the microwave to warm it up. Like, leftover pizza microwaved is kind of soggy and steamed because it's literally steamed, right? All you're doing in the microwave is heating up the water and boiling the water, and then the water turns to steam. The steam warms up the bread and the meat and the cheese and whatever else is on the pizza. But the whole thing is kind of soggy, because it literally is. Right? So what use do we find microwaves? Heating up food. What use do we find radio waves? Well, communication, right? Radio stations, TV stations, cell phone signals, Wi-Fi signals, they're all done in the radio, at different frequencies in the radio spectrum. Okay. What has more energy? Radio waves or visible light? Well, energy, right? Remember that energy is proportional to frequency, right? Higher energy means higher frequency. So which one has more energy? The light that has more energy will have higher frequency. What's higher frequency? Visible light is. What'll do more damage to your body? Well, if visible light photons have more energy, then when a photon with more energy hits your body, it could, if a photon has enough energy, it could break a molecular bond. It could drive a chemical reaction in your body. And, not like one photon hitting your body could do that much damage, but if you get hit by lots and lots of high energy photons, that could break enough molecular bonds to really do some damage in your body. Visible light photons don't have that much energy, so the odds of, visible light hitting you, the odds of that doing damage is pretty low, but they have more energy than the radio waves, right? Radio waves hitting your body is harmless because radio photons have so little energy, they can't really do anything to your body, right? So it doesn't really matter how many photons. That's one of the interesting things, is that because light is broken up into those particles, into photons, and the energy of a photon only depends on frequency, it doesn't matter how many radio photons hit your body, because each of those photons has so little energy that they can't do anything. So whether your body is hit by 1 radio photon or 1 billion radio photons, they are equally harmless. Right? As opposed to ultraviolet light, right? Ultraviolet light has more energy than visible light. It has higher frequency than the visible light. And so, a lot of visible light hitting your body, not very harmful, right? If you stay inside all day with light bulbs on and those light bulbs are shining visible light at you, pretty harmless. But the higher the energy of the photon, the more damage it could do because it has more energy. And so a bunch of ultraviolet light hits you, each of those ultraviolet photons has more energy, and it could potentially do some damage, right? Like I said, a single ultraviolet photon hitting your body is not going to do a lot of damage, but if each ultraviolet photon could do damage, and then you're hit by a lot of ultraviolet photons, then the odds of it doing damage go up pretty well, which is why ultraviolet light causes sunburns. X-rays have even more energy because they have even higher frequency. And so X-rays have so much energy, they can punch through your soft tissue, which is why when you take an image, when you take a photograph of something when it's being bombarded by X-rays, the only thing in your body dense enough to stop the X-rays is bone, right? All the skin and all the soft tissue lets the high energy X-rays go right through. And so that's what an X-ray image is, right? An X-ray image is basically a silhouette of your bones, because the bones are the only things that stopped the X-rays. And I guess teeth, too, when you get dental X-rays, right? Your teeth are dense enough to stop the X-rays also. Gamma rays are the highest frequency, highest energy light. gamma ray photons have so much energy, they can punch right through your body. They can go right through even the bone. Right? So, what kind of light is going to be the most harmful? It'll be the highest energy. It'll be the gamma rays. Which of the three properties of light is responsible for the damage? It's going to be the energy. Right? Because when a photon hits you, right? When a photon hits your body and your body absorbs that photon, like the photon is gone. The photon was destroyed, essentially. The photon disappears. Why did the photon disappear? Because, the particles in your body absorbed the photon and absorbed its energy. And where did that energy go, right? Energy can't just disappear from the universe. The number one law of physics is that energy doesn't disappear from the universe and energy doesn't appear out of nowhere. So if your body absorbs energy, that energy has to go somewhere. It has to do something. And one of the things the energy can do when you absorb it is it could break molecular bonds. It could disrupt genetic code. And, if you have a high energy photon like an X-ray or a gamma ray punch its way into your cell nucleus and drive a chemical reaction that breaks a bond in your DNA, then that could cause a mutation. And, a random mutation happening in a random place probably won't do anything. But if your body is hit by a lot of gamma rays in a short period of time, then the odds of one of those gamma rays driving a bad mutation goes up. It's not guaranteed, but the odds go up. It's a game of statistics. It's a game of odds. And statistically, if you get hit by enough X-rays or gamma rays all at the same time, one of those gamma rays could cause cancer. Right? This is why you don't want to have to go to a doctor's office. You don't want to have to go to a doctor's office and get too many X-rays one after the other, because the more X-rays you get, like, the odds go up. Not that it's guaranteed. It's not 100% guarantee that you're going to get cancer, but, every time you go to an X-ray, every time you get an X-ray, the odds go up just a little bit. And that's why, doctors have to be trained on that, right? Doctors have to be trained on what's the safe amount of X-rays to give somebody. Okay. So, we can connect the dots here, right? Here, I'll, in the practice page, right? Which of these types is seen by our eyes? Visible light. Which of them has the highest energy? Well, the highest energy comes from the highest frequency, so that's gamma rays. Which type of light can our bones cast shadows with? I suppose is the conjunction I'm looking for. Right, that's X-rays. Right. Which one of these boils food? Well, food boils at the right frequency in the microwave part of the spectrum. Which one has the longest wavelength? That's the radio. Causes sunburns? That's... Where did that go? Ultraviolet. Right? And then, which ones do we perceive as heat? Infrared it is. Alright. And then which type of light travels the fastest? I hope I didn't trick you this time, right? They all travel at the same speed, right? All light, regardless of wavelength, regardless of frequency, all light travel at the same speed. They're all the same. Right? This seems a little counterintuitive, right? But it's worth remembering. The speed of light doesn't come from energy, right? High energy light, low energy light, it's all carried. Those light waves are carried by the electromagnetic field at the same speed, right? The wavelength goes up, the frequency goes down, but the speed's all the same. right? Higher energy light doesn't travel faster. It just has higher frequency. Okay. And this becomes really important because when you're talking about viewing things from very, very far away, like stars or galaxies, right? Then light travels through space at the same speed, right? The light, if a star gives off blue light, red light, and ultraviolet light, right? All of those different energies of light, all those different wavelengths of light, they're all traveling from the star to us at the same speed. And so they're all going to arrive here on Earth at the same time. It's not like the higher energy light gets here first because it traveled faster. Which is good, because if that were the case, astronomy would be a lot harder. Okay. All right. I think that was probably pretty easy for you. And so you're ready to go on to the next thing. All right. Bye.